So let's calculate the derivative of this function f of x equals 3 divided by x, where x equals 3, and then give the equation of the tangent line. Okay, so we have that by the definition of the derivative, we have f prime of 3, that's the derivative of f at the point where x equals 3, is going to be, I first take a nearby point x comma f of x, and I calculate the slope of the secant line. So that's f of x, the difference in the y values, f of x minus f of 3, divided by the difference in the x values, x minus 3, and I take the limit of that as x approaches 3. Okay, so we're going to calculate that. F of x is 3 divided by x, so this is the limit as x approaches 3. F of x is 3 divided by x, minus f of 3 is 3 divided by 3, divided by x minus 3. Simplify this a little bit. This is the limit as x approaches 3 of 3 over x minus 1 divided by x minus 3. Let's go ahead and multiply numerator and denominator by x in order to get rid of that fraction inside of a fraction. So this is now the limit as x approaches 3 of 3 minus x divided by x minus 3 times x. And I'm not going to multiply that through in the denominator a lot because I want this to simplify. Okay, now calculating that limit, of course, we should try direct substitution, and it's not going to work. It's going to give us a 0 in the numerator and denominator. So that tells us that we should be able to mess around with it and simplify. And you might see that the numerator has a 3 minus x and the denominator has an x minus 3. They look very similar, but those two expressions are opposites. So in order to make this work, we can factor out a -1, say, from the numerator. That's going to be the same, 3 minus x is the same as -1 times x minus 3. Divided by x minus 3 times x, and we're taking the limit of this as x goes to 3. And now I can cancel that common factor of x minus 3, and I get the limit as x approaches 3 of -1 divided by x. Okay, and now I can use direct substitution. It looks like that limit is -1/3. Okay, so we have f prime of 3 is -1/3. That is the slope of the tangent line to this function, of the graph of this function, f of x equals 3 over x, at the point x equals 3. This is the slope of the tangent line to the graph of f. And I'm going to say at the point, well, if x equals 3, the y-coordinate is 3 divided by 3, so that's 3, 1. And so the thing we're supposed to do is we're supposed to give the equation of the tangent line. So we have the slope is -1/3, and it passes through the point 3, 1. So that tells us we can now write the equation of the tangent line is y equals, well, we could start at our starting output value 1, and then we have our next output value is going to vary by -1/3 times the distance from our starting x value, so x minus 3. So that could be our equation of our tangent line. And I just want to go ahead and take a look at Desmos to see how that works. Here's the graph of f of x equals 3 divided by x. And I just wanted to kind of reiterate the slope of the tangent line, or the tangent line here is the line that this graph looks like if I zoom way in. And you can see that if I zoom way in to the point 3, 1, eventually that curve does look like a straight line. And I can turn on the grid and see what does it look like the slope is. The slope is definitely negative. And you might wonder if this is a fair look at this point. And you can kind of see that the distance, this square is 2/1000ths of the point, and this distance is also 2/1000ths of a point, and these are not square. So I can actually, I'm going to use Desmos and say zoom square. So now it's actually square, and I can look and see the line that this graph looks like. It does look very much like it has a slope of -1/3, because I can go from here to this point over here, and it looks like I'm going down 1 over 3, down 1 and to the right 3, down 1 and to the right 3. So this looks very much like a slope of -1/3. So let me zoom back out, and I am going to put in the equation that we found. It was 1 minus 1/3 times x minus 3. And there is my line that looks like very much like a tangent line. Looks good. If I zoom way into the point, then I cannot tell the difference between my original graph in blue and the tangent line in green. Okay, great. Now I want to go back to the notebook, and I want to point out there are actually two common versions of calculating derivatives. So this is the one that we have seen already, where we take f prime of a is the limit as x approaches a of f of x minus f of a divided by x minus a. And the idea of this is we take some nearby point with input value of x, and then that tells us that I'm looking at this point x comma f of x, and our point of interest is the a comma f of a. And I'm looking at the slope of the secant line is the difference in y values divided by difference in x values, so f of x minus f of a divided by x minus a. And I take the limit of that as x approaches a. Now, another way to think about this, since I'm really centered around this point, this input value a, instead of calling this other point, this other input value x, I'm going to say it's a plus a little bit. And for some reason, it is very common in calculus books to refer to that plus a little bit as an h. Okay, so the h is the distance between a and that nearby point. And I want to point out h might be negative. In this case, I have drawn h as a positive value, but I can also take h as a negative value, and this could be a plus h, and I could be looking at this point here. But I'm not going to bother with that. So keep in mind that h can be a negative value too. But in that case, what I have is this point is, well, the x-coordinate is a plus h, and the y-coordinate is going to be f of a plus h. And now my f prime of a is going to be, again, a limit, and I'm just going to write the limit, but we're going to think about what the limit is. And I'm going to take the difference in y values, f of a plus h, minus f of a divided by the difference in x values. That's a plus h minus a is h, which should make sense because I chose h to be that little difference of x values. Okay, and in this case, if I'm thinking about sending a plus h to a, that is the same thing as taking a limit as h approaches 0. Okay, moving that input a plus h towards a is the same thing as moving h towards 0. So let's take a look at that same problem where I'm calculating f prime of 3, where f of x equals 3 divided by x. And let's use that other equation. So let's look at this again. So this is f prime of 3. By that other equation is going to be, I'm going to calculate f of 3 plus h minus f of 3 divided by h. This is my, I have 3 f of 3 as one point, and then 3 plus h and f of 3 plus h is another point, and I'm going to take a limit as h goes to 0. Okay, so this is going to be the limit as h goes to 0. F of 3 plus h. F of x is 3 divided by x, so that's going to be 3 divided by 3 plus h minus f of 3, again, is 1. It's 3 divided by 3. All divided by h. So limit as h goes to 0, I'm going to say this is 3 divided by 3 plus h minus 1 all over h. And now I'm going to, again, to get rid of the fractions within a fraction, I'm going to multiply by that denominator, 3 plus h divided by 3 plus h. And this is going to now be the limit as h goes to 0 of 3 minus 1 times 3 plus h is 3 plus h divided by h times 3 plus h. Let's come back up here. This is the limit as h goes to 0 of 3 minus h divided by h times 3 plus h. The limit as h goes to 0 of negative h divided by h times 3 plus h. And the nice thing about this here is, in this particular case, I have my common factor of h is already there. And that's the thing that causes both numerator and denominator to be 0. So I can cancel that, and I get the limit as h goes to 0 of negative 1 divided by 3 plus h. And I can do this by direct substitution. I get negative 1/3. This is the same calculation we did before. We again get f prime of 3 equals negative 1/3. So I just wanted you to know that there are two ways that are often used to calculate the derivative. Sometimes one way feels more convenient than the other. And there's no real way to say exactly when one version feels more convenient than the other in any given case. But they're both doing exactly the same thing. It's just in one case we call this nearby point x, and the other case where we call this nearby point a plus h. And when we call it x, then we're taking a limit as x approaches a. When we call it a plus h, it's saying it's a plus a little bit, and we're taking a limit as that little bit goes to 0.